Welcome back to ECE 442-542. We are almost a week away from exam number one. Exam number one is a week from Wednesday, and make sure that you're ready for that. If you're an online student, you have different ways of taking the exam. Today we are actually talking about frequency response, which we're jumping a little bit of ahead in the chapters that I'm providing or the notes that I'm providing. Today's class, you could read up on that in section 5 of chapter 4. And we've covered chapter 3, which was Z-transforms, after exam 2, but Wednesday's lecture, we will begin unit 3, which is inverting these Z-transforms, and that's when the region of convergence becomes more important. We need the region of convergence to be able to tell us which particular sequence in the time domain we are dealing with. We could have different sequences depending on the region of convergence. So we need the region of convergence along with the transform in order to obtain a unique time sequence. That's the value behind the region of convergence. That's why we're talking about the region of convergence. If you haven't yet completed homework number 2, that is due on Wednesday. And there is an additional write-up underneath the homework assignment if you're struggling with one of the, I think it's transfer function to state space. I'm not sure which problem that is, maybe problem 3. Look at those additional notes, and hopefully that will help step you through that process a little bit more. Likewise, if you want to find the Z-transform of an exponentially damped sinusoid, which is one of the homework problems, I provide you with a lecture on doing it for a cosine. So the process for the sinusoid exponentially damped should be fairly straightforward, or a connection quite readily made between the additional material that's provided in D2L and that homework problem. We will have an exam review session on Wednesday following our normal class period. We won't use a class period for that, but even though we have the room reserved, I can't guarantee you that the exterior doors will be open. If you're going to the restroom, make sure you have somebody ready to let you back in, or if you're coming late, make sure you have the ability to signal someone, hey, I'm downstairs, I'm outside, get me in the building. We will have access to the room, but I can't guarantee that the exterior doors will be open. So somehow, yeah, we may have to have a secret knock, which I don't think I can hear, but maybe you can have a classmate that's tuned in to that particular knock, just as a forewarning. I always get a little nervous when students leave the room now during class. I'm not sure when the outside doors lock, but I have seen some of you return from, let's say, a restroom break, but I always get a little nervous when you do leave the room, since we are sort of after hours. So if you see me looking a little anxious, it's not because you left, it's because I'm afraid you may not be able to get back in. As I indicated, today's talk, or our exchange, is frequency response. And when you hear that for the continuous time, you may immediately start thinking Bode plot. We can obtain a Bode plot for the Z-transforms that we're dealing with, but that's a little ornery or a little more involved, so it's easier to just have MATLAB do the Bode plots for us. But we can do it analytically, and we can do it graphically from the pole zero diagram. And so we'll step through that today, and we'll try to still make the connection. I left you with color between the lines after class, and I didn't fill them in last time. Maybe you did. I think coloring now is a soothing experience from what I've been told. So now maybe you can color in those notes that I provided, just sketches for at the end of last lecture, but we'll try to fill them in this lecture. Question?
For exam 1, where's the cap at? Is it today or tomorrow?
The cutoff for material on exam number 1, what is that? That was your question, I think. That's today. After today, well, I shouldn't say that, but the lecture material for today is the stopping place for exam number 1. Homework number 2 is obviously included, that material. So if you turn that in on Wednesday, that's still exam number 1 material. The lecture content for Wednesday, I hope, will be new material. That will be starting Unit 3, which you will find in Unit 3's module on D2L. You'll have to see it other than in Unit 2, and I think now you're getting the hang of where to look. Look for Wednesday's material. Obviously, the Exam 1 review material I'll probably put in the Exam 1 module. So I'll try to record that and make that available to you. If you have questions, somebody I think has already copied the entire review topics and plopped those in as a question in the quiz but if you have more specific information that you want covered, let me know and we'll try to direct our review, but I will probably just work problems from previous or practice exams. Maybe focused on if you have questions. Here today, what we want to do to finish up material prior to exam number 1 is talk about frequency response, and we'll try to make the connection with the continuous time case. And here's sort of the steps. That h of z, with that vertical line, typically I would have the z format a little bit lower than on the same line. It would be a vertical line, and then below that or next to it, z equal e to the j theta. We're now replacing z with this complex number, e to the j theta, and we're now think of theta like you thought of omega when you looked at h of j omega for the frequency response. Let me give you sort of a big picture view. Hopefully you're familiar with the continuous time case, which is on the left. H of s evaluated at s equal j omega. That gives us then h of j omega, and we can find that many different ways. You could analytically compute that. You could sketch the Bode plot. You could also find h of j omega based on this pole 0 plot in the S-plane. That's what's here. And we're really just evaluating the transfer function, h of s, along that blue shaded positive imaginary axis in the S-plane. That's what gives us h of j omega, the evaluation of h of s along that imaginary axis. What would happen then, or what's the connection that we've already talked about in previous lectures that allows us to connect s with z? What's the relationship? Z equals e to the st. So that's what I'm using here. And we've now replaced s with s equal to j omega to obtain the frequency response. And if we do that, we really have this is e to the j theta. Maybe this is confusing to put it down there. So let me just say that this vertical bar, we're evaluating for z equal to e to the st, but we're replacing s with j omega. So now we're evaluating h at e to the j omega t, and we actually combine or consolidate omega t into one variable and call it theta. That's actually an angle. Omega t is radians per second. T is the sample period, seconds. We multiply those together and we get radians. The generic units then for theta is radians. E to the j theta. And we all are very familiar with Euler, and we know that e to the j theta, the magnitude of that for any value of theta is 1. And we'll maybe walk through that in a minute. But that means now the frequency response for h of z is determined by evaluating h of z around the unit circle, from starting at z equal to +1 and marching around in angle, theta, from 0, theta equal to 0, all the way up to theta equal to pi, taking us all the way over to -1. So we might think of -1 being a high frequency. Why is that? Well, that's what we're doing in this mapping. And we won't get there really necessarily today, but you can start to maybe think about, well, what frequencies really do we have access to when we sample something? We actually only get up to frequencies equal to half of the sample frequency, omega sub s over 2. That actually puts us around to this point of -1. Then we just keep sort of, well, the bottom half of that is like the bottom half of the imaginary axis, negative frequencies. That's what we have in the bottom half of the unit circle. So it's really not giving us any new information. And if we just keep circling around, we just see the same frequency response for higher frequencies. They really just map or alias down to 0 to omega sub s over 2. We'll get a little bit more insight into that. The main thing today is to realize that we want to now evaluate h of z along the unit circle, or as we pass along the unit circle from s equals 0, omega equals 0, or theta equals 0, which is z equal 1, up through theta equal to pi over 2, which now we're at j, and then all the way over to theta equal pi. Now we're over to z equal -1. That's sort of the big picture view of what we are after. Let's now return our thought process so that we connect with what we're used to seeing. Let's now remind ourselves what happens, or how we find the frequency response for a continuous time transfer function, h of s. And before I had somebody ask about how did we get tau, or why did we put our pole at 600, remember we wanted to have a bandwidth of 100 hertz. We want a bandwidth then in radians per second of 2 pi 100, and we simply rounded pi to 3 so that we have 6 times 100, that's 600. That's the pole's location, and that gives us our bandwidth of a first order low pass filter, having a bandwidth of 100 hertz. How do we sketch that now in the Bode plot? The Bode plot has two pieces. How do we sketch the magnitude piece? Or what do we sketch? And I've already labeled it. That's sort of a hint, I hope. We have our transfer function now is 1 over s over 600 plus 1. What form is that written in? It's kind of confusing a little bit, but it's really tau s plus 1. That's time constant form. We've normalized the constant, which is 2, 1. That's time constant form. We've factored out we've made the tau explicit, but in fact, we've written tau as 1 over the pole. And so we can actually see the pole at 600 in this time constant form. You could multiply by 600 over 600 or multiply by 1 to actually obtain so this is our time constant form. And that's the form we use for sketching the Bode plot. If we multiplied this by 1, now you can definitely, I hope, see where the pole is located. It's at the location that causes the denominator to vanish, and that's when s is equal to minus 600. If that's the case, how do we sketch the magnitude plot for this transfer function?
At s equals 600, or at a log of omega equals 600, it goes down 22 per decade.
So now we're claiming that we have the answer was we go down at 600. Where did I start? Why did I start there? Do I start there, or do I start here? Do I start here? Do I start there? Where do I start for low frequencies? 0 dB, because I have a DC gain of 1, and log of 1 is 0. That's why I was starting that break at 600 from 0 dB. This is because h of 0 was equal to 1. And in dB, that gives us 0 dB. And this particular drop-off or roll-off is due to just one pole. This is now minus 20 dB per decade. Or if we wanted to resolve that in finer intervals of frequency, we might say, oh, that's the equivalent to minus 6 dB per octave, where octave now is a factor of 2, decade is a factor of 10. What's our phase curve look like? Question? 6 dB per octave, that's minus 6 dB per factor of 2. If we're starting at 600, then I could walk over to 2 times that, or 1200, and then I would be down 6 dB from where I was at 600. In this case, it would be at minus 6 dB, because I started at 0. If I went a complete decade, which is typically what we think, I would go down from 6,000, which is a decade beyond 600, and say, oh, I need to be down at minus 20 dB. And that way I can now connect these 2 points. I'm at 0 dB at 600. I'm at minus 20 dB at 6,000. Now I use that to draw my magnitude curve, and it doesn't change slope at any time thereafter, because I simply have the one pole at 600. So those are just equivalent slopes that we will agree are equivalent. So if somebody now wanted to say, well, what's happening at 900? Now you could maybe start chopping that up in factors of 2 instead of factors of 10 to see where am I in terms of magnitude. I know every factor of 2 I'm changing by 6 dB. What's the phase curve look like for this low-pass filter? Is it 0 at 600? Or what would you maybe do? I might look at extremes. I might look at H and say, what are some extreme cases? And I'm looking at H of j omega, so I'm really looking at replacing S with j omega, and I'd say, well, 0 is pretty extreme. That's DC. What's my angle when S or j omega, when omega is 0? What's my angle? Then I have, what's my angle of 1 in the numerator? That's a complex number. It has a value of 1. What's the angle of 1? 0. If you now walked to location 1 in the complex S-plane and you said, what angle, if I was standing at the origin, what angle did I have to turn through to see you at 1? I wouldn't have to turn at all. I would be turning 0 degrees. Then I would say, well, what happens when S is equal to a really big value, or J when omega is a really big value? Then the denominator, the 1 is still 0 degrees. My denominator angle is changing. Now it's J something big over 600. That's still J something big plus 1. I have 1 for a real part, and I go really far up, J something big in the vertical direction. What's my angle due to that denominator factor? 90 degrees. I would have to turn to 90 degrees to see you. Well, because it's in the basement, I'm subtracting that because it's now an exponent. I now have minus 90 degrees. So I found two extremes. I know that I'm starting for low values at 0. Whoops. And at big values, I'm going to minus 90. Now, how do I connect those? Here, we just agree in this straight line sketch that we are centering this 90-degree change, which is 0 to minus 90, over the break, or centering it on the break frequency, which the break frequency is the pole location, 600. We're centering minus 90-degree change with a straight line over the 2 decades bordering 600. We'll go all the way to 60 with 0 degrees. We will go all the way back to 6,000 at minus 90, and then we'll just get out our ruler and draw a straight line. Can I just sit in awe of that straight line? I couldn't believe that that was done. I sort of was standing on my head drawing that, if you were paying attention, but I'm kind of impressed that I was able to do that without too many jiggles. But this now tells us that, what is that value? This is now minus 45 degrees. We're now sloping at minus 45 degrees per decade. And over a 2-decade interval, that says we're changing angle by 90 degrees. And since it's from the pole, we're going down. That's now our Bode plot. Why do we care? Well, now we could answer anyone's question if they said, I'm going to shake your system with an input at some frequency, and you now have a continuous time system. That's the low-pass filter H of S. What's the output going to do? That's what the Bode plot allows us to determine for any omega. If we now walk up and shake the system, it's a linear system. Suppose we now shake it at 500 what? What are the units on 500? That's radians per second, isn't it? Because when we multiply by time, we need radians for that argument. So if you wanted to factor out in hertz, you would divide that by 2 pi to find its frequency in hertz. Now we're shaking this pretty violently in terms of frequency, 500 radians per second. Maybe not that. It's not quite 100 hertz, is it? 100 hertz was a little bit more than 600, 628. So we're not shaking it quite at 100 hertz, but that's pretty fast in terms of something physical. And we're doing that shaking with an amplitude of 2. So we're going plus 2 minus 2 at a frequency of 500 radians per second. And we want to know, we've put in this input, what's going to be our output in the sinusoidal steady state, which means we're going to wait until all the transients have decayed and just say, okay, you're shaking. How are you shaking? All the transients have disappeared. And how long do we have to wait for those transients to disappear? 2 days, 3 weeks, a month, 5 tau, 5 time constants. You find your slowest pole, determine its time constant, and say, oh, I need to wait 5 of those, and after that, I'm in steady state. The O is now output. The SS is sinusoidal steady state. What's the structure of that output? Do you remember? Do you remember what the frequency is? If I'm shaking it at 500 radians per second, and this is a linear system, what's the frequency of the output? The same frequency. It's 500. So we could write down cosine of 500t. We know that. If this is now, if we say this is omega 1, we know that we're going to have omega 1 as the same frequency that we're shaking. We started with a magnitude of 2. That's this. Does that get changed? Well, in fact, if we went up here, we would find 500 and say, well, this is really, I'm not so impressed with that, but that's supposed to be a vertical line, and this is now at omega equal to 500. And we would say, oh, here is how the magnitude gets adjusted, and here is how the phase gets changed. As I pass through this linear system that has this for its frequency response. Now remember, these are straight line approximations. So the true curve, magnitude curve, and the true phase curve will be curved. The phase will still go through minus 45 at 600, but it's going to be curved a little bit. It'll be 6 degrees off at the upper and lower limit, and my magnitude plot will be how far down below 0 dB really at 600. That's the half power point, or the minus 3 dB point. So you will actually be 3 dB below 600 at, 3 dB below 0 dB at 600 radians per second. But we're just drawing the straight line plot here. Yes?
And that's just because that's a pole frequency?
So this pole will be, if it was a 0, if we were going up, we would actually be at plus 3 dB. So the error in your, and this is for a single factor, if it was a repeated pole at the same frequency, you would have double that error at that location. Now, where was I? Trying to find the structure. We know we're shaking at 500. How do we change, or do we need to change? Does our magnitude change? Well, from our straight line sketch, it really doesn't, but it is a little bit. It's going to be modified. And how do we denote that in this expression? What's our notation that we use? Do you remember that we might say, oh, that's the magnitude of h. What do I put in there? J omega 1, and omega 1 is 500. We just find the frequency response, or we evaluate h at J500. That'll be a complex number. We find its magnitude, and that's what scales the original magnitude of 2 at the output. Do we do anything more? Are our peaks aligned? Are peaks and valleys aligned in the input and the output? Are they? Generically, no, they are not, and this actually tells us they definitely are not. It's closer to minus 45 than to 0. So in fact, this is going to be adjusted by the angle or the phase of h at J500, where this is omega 1 and this is omega 1. So we need to find h of J500. And what are some ways to do that? We could find it analytically. That just means we would plug in everywhere we had an S, we would replace S with J500 and compute the complex number that results, and then find the magnitude and angle of that complex number. A lot of calculators do that for you. We could do it graphically. We just did it with our straight line Bode plot, or we could do it with a pole zero diagram. And that's what we're going to show now, because that's the one we're going to use for the discrete time frequency response. That one is easier to sort of think about in the z-plane. Let's now find h of J500 using the pole zero diagram. And I'm now going to say that those tick marks are at 600 away from the origin. This is now minus 600, and this is J600. Did I do the right distance? Distance always looks more impressive vertical than it does on the floor, right? If you said 10 feet in front of me doesn't look very far, but boy, when you look up, it's pretty far up. Anyway, to dunk or do something. All right, where were we? Trying to sketch. We now know that we have a pole right there. And we would put all of our poles and zeros on this diagram. We go up only to 500. Let me just say that's that point. And in fact, we could now say, oh, the contribution of that factor due to the pole is going to be found by measuring that hypotenuse value, L sub p, and the angle, theta sub p. And that's what will actually be found graphically in the denominator in our pole zero form of this transfer function. So really we're saying we have h of s when we evaluate s at J500. And what did we have in the numerator of this transfer function? Let's say now it's in pole zero form. Since that's the diagram that we're creating, we had a numerator of 600 in our pole zero form. Maybe I should have labeled that up here, and I don't know if I did. This is our pole zero form. And we're replacing S with J500, which means then down here we have J500 plus 600. And that's typically not how we view a complex number. We usually have real plus imaginary, but you can interchange those. Or now this is now 600 over L sub p at an angle of theta p. This pole factor we can actually find graphically from our plot. If we've drawn the plot properly to keep all the distances correct, then we can actually measure angles from that. We haven't changed the scaling on the horizontal or vertical axis. They're the same. What would you expect theta sub p to be relative to a common angle? Is it at 45? Is it above 45? Is it less than 45? It's less than 45. You can see that from this. We're not quite to J600. And we know that the magnitude of L sub p is not quite the square root of 2 times 600. So we can now find that. We can now say analytically this is now 600 over the magnitude of 600 plus J500. That's L sub p, and the angle is the inverse tangent of vertical over horizontal. And if you compute those numbers, this distance or magnitude is 781, and the angle is almost 40 degrees, 39.8, so that now if we divide 600 by 781, we end up with 0.768, and that angle, when it does come upstairs, we have an angle of 0 upstairs. We subtract the angles in the denominator, and we have minus 39.8 degrees. Or in fact, now we can write down V sub O, the output in sinusoidal steady state, is going to be 2 times 0.768 cosine 500t minus 39.8 degrees. The convention is to mix the units in the argument of the cosine. The first unit is radians per second times second. That's in radians minus something in degrees. We just can think in degrees cleaner. But if you're combining those and computing a cosine, you need to make sure that your angles are consistent. Either they're both radians or they're both degrees. That means that our peaks and valleys are offset by about 40 degrees. The output is lagging behind the input by 40 degrees. Our peaks and valleys and what's our amplitude? The amplitude is 76% or 77% of where we started. We've collapsed a little bit. This is now roughly 1.536 instead of 2. In general, for any input, we have this. Once the transients are gone, then we have our sinusoidal response. And we adjust the amplitude based on the magnitude of our transfer function at the frequency that we're shaking at, omega 1, and the phase, the peaks and valleys, are offset by the angle of that transfer function at j omega 1. And we know how to find those. We simply evaluate our transfer function at that location on the imaginary axis, j omega 1. And I think I've drawn a generic case. Here we might have a P1, that's the first pole on the real line, real axis, negative real axis. Is that system stable? This is the S-plane. All of the X's are not in Texas, but they're in the left half plane, so it's good. It is a stable transfer function. And we could individually find these pieces, the magnitudes of each of these factors from the poles and zeros to that frequency, j omega 1. Those are the L's. We have an L sub z for the single zero, and then we have 3 lengths. We have 3 pole angles, and we have 1 zero angle, and we might have a gain alpha that we have to keep track of. In our example, that alpha was 600 when in the pole zero form. To find the magnitude, we would just, and if you had a ruler or dividers, how many know what I mean when I say dividers? Okay, well, back in the day when you were drafting or drawing, you might have dividers, and they were, well, I can't even explain it, but essentially it's a way of measuring length or distance, and they have very sharp pins on the ends. So when I was drafting in high school, back in the day, my teacher would throw, that's like 2 darts coming at you. You wanted to behave in that class. Okay, so if you were cutting up, being a little ornery, you might end up with dividers in some part of your anatomy. In your arm or neck or somewhere. Maybe a piercing then. You went home one day and I was bleeding and Mom said, what's that? Did you get in a fight? No. Let's not talk about it. No. And the angle, the phase. You could measure with a protractor. How many know what a protractor is? There we go. Thank you. So I'm not going to explain that. And what do you have? You have your zero angles, theta sub z, and you take away, because the poles angles are downstairs, and really in a complex number, you could write those complex numbers as a magnitude e to the j theta. Then what happens when you combine all of those? You're combining the exponents, the e to the j thetas. You have e to the j theta z upstairs. You have all these e to the j theta p's downstairs, and when you pull them all together, that's how the subtraction comes into play for your pole angles.
Is h of j omega 1 supposed to equal like negative 180 or something?
So now h of j omega 1, I'm not quite sure. H of j omega 1 is going to be whatever it is at the frequency omega 1. So the magnitude and the angle, if you now had, I think I know what you're getting at, maybe, for high values of frequency. For high values of frequency, where would you think my angle ends up? Does it go to minus infinity? How many negative angles do I have? I have some minus 90s and I have some plus 90s. The plus 90s are due to the zeros. The minus 90s are due to the poles. I'm assuming I have linear factors. I have 3 poles, so that gives me minus 270. I have 1 0, that gives me plus 90. I combine those and I end up at high frequencies at a phase of minus 180 degrees. I think that's what you're asking. So at high frequencies, you will be at minus 180. At low frequencies, what are you? What's the phase of h of j0 at DC? It's 0, because the complex poles are conjugate pairs. The one upstairs cancels the one downstairs at 0, and so you're left with 0. The pole and 0 on the real axis are not giving you any angle contribution at j omega with omega equal to 0. And there would be an example if you wanted to go home and look at what's happening. In this case, most of those poles are right on top of each other. You could say, I have 3 poles. If you were just doing this real quick, back of the envelope, you might say, I have an s plus 2 in the denominator cubed. You could kind of say the 1 and the 3 are going to just bunch at 2, and then I have a 0 at 4. But if you're really being quick and dirty with trying to figure out what's going on. What happens in the discrete time case? Frequency response. It's very similar. That's why I made you struggle. That's why we worked through or discussed the continuous time case. But now when we shake this system, we are shaking it with omega t in, or we're just collapsing omega t into one variable we're calling theta. So now we're shaking that at theta 1. And that's radians per sample. And n is sample. So we're applying this sinusoid, the input sinusoid v sub I, to a linear system given by its transfer function h of z. And what we actually end up with after the transients, and when would we have a steady state response and when would we not have a steady state response? in the discrete time setting. When can we apply this formula, this V sub 0 steady state? When our system has all of its poles in the stable region of the z-plane. I'm not going to answer, but they're inside the unit circle. If all of your poles of h of z are inside the unit circle, then this is applicable. If you have one pole outside the unit circle and you start shaking this system, what's going to happen? Will you get to a steady state? No. You'll excite that unstable mode and it's going to go unbounded. You will not have a steady state response if you have an unstable pole. We clear on that? We're assuming then that h of z has all of its poles inside the unit circle, and now we need to find h of z when z is equal to e to the j theta 1. That will give us a complex number, and we can always find the magnitude and angle of that complex number and use that information in this expression, which is structurally very much alike, or very much like the continuous time. Our original amplitude, d, scaled by the magnitude of h at that frequency. Cosine, we haven't changed the frequency of excitation with a phase shift. What does Euler tell us about the magnitude of e to the j theta? Is it on the unit circle? What's e to the j theta? Written in rectangular form. Or Euler. That's cosine theta plus j sine theta. We now have cosine theta plus j sine theta. That's from our friend Euler. How do we find the magnitude? Well, we take the real part, square that, add that to the square of the imaginary part, and take the square root of that. We now have cosine squared theta plus sine squared of theta. And that, last time I checked, for every theta, that's equal to 1. In fact, we are on the unit circle. With e to the j theta. That means now if we had a generic example, do you see all the different poles I have here? I have a P1. I have a P sub 2 up here. I have a P sub 3, its conjugate. And I have a Z, and I better call that a Z1 because now we're playing in the Z plane and our variable is now Z. So we need to subscript for our zeros to keep them separate from just the variable Z. We now go to the appropriate theta 1. If you're shaking this system at omega, how do you get theta 1 from that omega? Remember, theta 1 was actually omega 1 times t. The structure of the result, once we've had, you take out your dividers, you measure those lengths, you'll get the L's, you measure the angles with your protractor, and now you have the magnitude and angle at that particular frequency. So let's go back to where we started where we were finishing up last time. Let's work it through for a low-pass filter. This low-pass filter had a bandwidth of 600 radians per second, which was about 100 hertz. About because we rounded pi from 3.14 to 3. And that gave us a nice round number of 600. So we would have to pick R and C in such a way to make our pole equal 600. And our pole is the reciprocal of that time constant. But we derived, or you could derive, that first order differential equation that governs the dynamics of that RC filter. Put in a input of 2 cosine of 500 and look at what results, and that's going to be 2 times this 0.768. Is that what it was? And then our angle was about 40 degrees. What happens in the discrete time case? We want to now obtain a difference equation from the differential equation. Here's the differential equation that we want to discretize. We want to now chop that up, sample it, and figure out, can we get a linear difference equation that will describe a first order low pass filter with a cutoff frequency of about 100 hertz? Once you have a difference equation, that will be pretty easy to just crunch numbers. You don't have to build this filter. You can now just put it in a spreadsheet if you wanted to and filter a signal. Because you now know what the input will be. You know how to weight these delayed versions of the output, etc. So let's now look at a discrete equivalent. And we'll go through many, many, many more discrete equivalent strategies. But here let's just look at a forward difference approximation. We're obtaining an approximation of the derivative. And we're doing it by looking forward in time. We're going to the next output value in time, n plus 1 capital T, from the present time, v sub 0 of nt. What's the change in time? Well, that's n plus 1 capital T minus nt. And that ends up being just capital T, one sample period. That's the delta T. That's how we can now change this first order differential equation into a linear difference equation. And the only thing left to do is to figure out what is T. What is our sample period? Do we just pull it out of thin air, or do we have a strategy? We know our bandwidth. The bandwidth of the continuous time filter was 600 radians per second. That's where the pole was. S was minus 600. What did we say we wanted to do? What was our rule of thumb? Did we talk about a rule of thumb for sampling? If you now say, oh, I have this signal in the continuous time setting and it has a frequency of 600 radians per second. How did we say we were going to chop that up or sample that? 3 times omega c? 5 times omega c? Okay, let's start. We'll do the auction thing here. We have 3. We got a 5. Got a 5. Anybody want to raise that bid? 30. Wow, sold to the gentleman wanting to do 30 times the sample. That was our rule of thumb. 30 times. It wasn't Nyquist. It wasn't 2 times. It was now 30. We're trying to really capture the shape of that signal. That's our rule of thumb. So now we know that if we're given a bandwidth, the highest frequency in our system, let's now sample at 30 times that. And this is just a rule of thumb. That's not a hard and fast. It could be 28. It could be 35. We're just saying this is a pretty good value. 30 times the highest frequency in your system. We just have one frequency in that system that has a low-pass filter of about 100 hertz for a bandwidth. This now ends up being 30 times 600, or 18,000 radians per second. That's our sampling frequency in radians per second. We wanted a capital T. We wanted the sample period, but we know omega sub s is 2 pi f sub s, and f sub s is the reciprocal of the sample period. F sub s is our sampling frequency in hertz. Omega sub s is our sampling frequency in radians per second. Capital T is our length of time in seconds between samples. Now we can solve that for T. T is now equal to 2 pi over omega sub s. And we already approximated omega c, so let's do the same kind of approximation here so that we are consistent. We approximated pi with 3 because here for omega sub s we had 2 times or what did we have? We have 18,000. So whatever we want to do for there, let's say that's now 6 times another 3,000. I just rewrote 18,000, factored it so that I could start canceling things. Or I now have T equaling 1 over, or 1/3, times 10 to the minus 3. And 1/3 is 0.333. And that's now the distance, or the seconds, in distance in time, seconds per sample. Or that's now 0.000333. That's what we would need to cut up our time axis into if we now wanted an input. Somebody gives you an input in continuous time, you would now need to sample that every 0.00033 seconds. That's now your input sequence of numbers in the discrete time system. That would be then what you might put into this spreadsheet if you've now put this. Well, we haven't yet made it to the difference equation, have we? I'm ahead of myself. Let's now find the difference equation. We can now convert the differential equation into a difference equation. We know tau, and we're approximating the derivative by this forward difference. The output at time t is just the output in the discrete time at little n capital T. The input at time t is just the input at time little n capital T. And the only difference between the differential equation and the difference equation is the approximation of the derivative with the forward difference. Meaning we're now saying the delta V naught is the V naught at time n plus 1 capital T from V naught at time nt. We can multiply and divide by T over tau, and that gets rid of the capital T in the denominator, and we can now start to combine common terms. We have two V naught terms, or we can now say that this is V naught of n plus 1 capital T equaling 1 minus T over tau V naught NT plus T over tau V naught NT. And what do we know? We know tau. Tau was our RC, and we picked that to be 1 over 600 for this bandwidth of about 100 hertz. Or this ends up being 0.00167, or 1.67 times 10 to the minus 3, now that I can kind of compare it with what I had before, and that's now 5/3 times 10 to the minus 3. And what was our T? T was this 0.333 times 10 to the minus 3, or this was the 1/3. The reason I'm writing that is so I can look at this ratio, capital T over tau. What's capital T over tau? All the 10 to the minus 3's cancel. The 3 in the denominator of the numerator and denominator cancel, and I'm left with 1/5, or 0.2. Do you see how I ended up with the boxed linear difference equation? I take 0.2 away from 1, that gives me 0.8. And my weighting on my input is capital T over tau, which is 0.2. Is that system stable? Well, if it's not clear yet, we should be able to figure it out in a minute, but in fact, this is in state space form if we wanted to think of it that way. It's a first order state space representation, and our system matrix, capital A, is 0.8. What's the eigenvalue of that capital A matrix? Capital A is 0.8. What's the eigenvalue of that matrix? 0.8. It's less than 1. It's stable. We would have expected that because we had a stable low-pass filter. Hopefully this discrete equivalent preserves stability. Some do not, but this one did for this simple case. So this now is if somebody now gave you a sequence of inputs, a sequence of numbers, and they said low-pass filter it, you could now apply that difference equation to that sequence of numbers. What would you have to know, though, about that sequence of numbers? That input string of numbers. That's the V sub I of NT. What would you have to know or say or be guaranteed in order for this to really make sense? You would now have to make sure that your samples of that continuous time waveform occurred at capital T intervals of time, the 0.000333. Every 0.000333 seconds, we would pull off that input's value. We would push it through this difference equation. So we're just combining previous values of the output with current values of, well, the input and output at the current time produces the output one time step into the future. And then we just keep cycling through that. If our input was 2 cosine of 500 nt, and t is now the 0.333 times 10 to the minus 3, then we do 500 times that t, and we end up with 0.1667 radians per sample. That's theta 1. Where our argument theta 1 was omega 1 capital T, can we find the sinusoidal steady state? Do you see how we're trying to use all these strategies that we've learned? Now we're going to a different representation of that same low-pass filter. Let's look at it in the frequency domain. Can we find a transfer function of this first-order linear difference equation? Can we find an h of z from this difference equation? And this is one of your homework problems, I think. Except there you're dealing with a DC motor, maybe, and you had to find a transfer function for it. What do we need to do? Well, let's just agree on some notation. Suppose that the z transform, that was supposed to be a z, that's now z of v sub 0 of z. If I gave you this, or if that was in the difference equation, what would that look like in the frequency domain? The z transform of a one sample delay of v sub 0. This would now be z to the minus 1 v sub 0 of z. And that one's hard because it's too easy. That we just have to hit the shift key. That's just a capital. This is now v sub 0 of z. And if we want the transfer function, what do we need to do about the initial conditions? If we're looking for the if we're looking for the transfer function, we can then neglect, that's why we didn't include them in these expressions. Normally you would have some maybe delayed terms or some constants added to those when you z transform. So now the z transform is neglecting the ICs because we are interested in the transfer function. What do we do? Now we can z transform that difference equation. The left-hand side in the frequency domain becomes z, capital V sub 0 of z, equaling 0.8 as a constant. That can slide outside the z transform. V sub 0 of z plus 0.2 v sub I of z. Or we can combine the output variable terms and the input is just one term, and we end up then with a v sub 0 of z equaling 0.2 over z minus 0.8 and this is our transfer function for the discrete time first order low pass filter with a bandwidth of about 100 Hertz and a sample period, capital T, or a sample frequency. The sample frequency was 18,000 radians per second. The sample period, capital T, was the 0.333 times 10 to the minus 3. That resulted in this transfer function. Now, we want to find h of z when let's say omega is 500. Omega 1 was 500. The sample period t, this is now our theta 1, where this was now omega 1 t, and this was 500 times the t, where the t and the 0.1667 radians that's 1/6. If we wanted to be thinking about how big that angle is, we could convert it to degrees. Or we're looking roughly at 10 degrees. Or if, well, yeah, that's close enough. So there is our 10 degrees for theta 1. We now want to evaluate, and what's our pole zero pattern look like for this system? Do we have any zeros? Do we have any open circles? Do we have any x's? And where is it? It's now there at 0.8. We now need to find this particular angle, theta P1, and this length is LP1, if you can see that. So that distance from the x to the point on the unit circle defined by j theta 1, that's e to the j theta 1. The angle, maybe I should say this. This is now e to the j theta 1. That's z. That's the value of z that we are evaluating that at. And here is our structure. If we now let z equal e to the j theta 1, what's h of z? Or this is now, I don't want green. And that's in radians, which is about 10 degrees. Yes?
So, I just want to take it back a little. After we found the transfer function, we found h of z. How and why did we introduce that j theta 1 value?
So now the question was, I think you're okay with this transfer function, h of z. But then you were saying, where did this theta 1 come from? Well, that came from this that we'd already kind of done on the side, or before. We had said, oh, we have a 2 cosine of 500 little t. We've now discretized that. We replaced little t with little n capital T, put the big T in with the omega 1. So that's 500 times t. That gives us the 0.1667. That's our theta 1 times n. That's based on a sample period of 0.333 times 10 to the minus 3. That help? That gives us now our e to the j theta 1 location. We can now find that analytically. Here we could say, oh, that's 0.2, that's our numerator. Then we have e to the j 0.1667 minus 0.8. We've simply replaced z with e to the j 0.1667. And by Euler, we can find the rectangular form of that. So now we have the cosine of 0.1667 plus j sine of 0.1667, and make sure your calculator knows that's in radians, or you convert it to degrees. And you end up now, this becomes 0.9861, almost 1, which you expected. This is now 0.1659. Or you end up with 0.8 at an angle of minus 41.71 degrees. Leaving you with now a sinusoidal steady state output of 2 times that change of 0.8 cosine of 0.1667 in minus 41.71 degrees. And this is 1.6, and you could compare that with what we had in the continuous time case. That should finish up this frequency. It went kind of quick at the end, but I hope you kind of know where all the dots are that you can now connect and color in. So we'll pick up with new material next time with the inverse C transform.